Hi everybody, welcome to the week 5 summary. Today we're going to have a look at solving equations graphically. We've been doing a lot of our solutions through algebra so far, so now we're going to have a look at how we can relate that to the graphs. And in terms of that, we're going to look at distance time graphs and break-even analysis. And then we're going to do just a quick summary of kind of linear modeling concepts that you've dealt with during week 5. So first thing, solving equations graphically. So here the first thing to look at is that solutions are given by the coordinates of points on the line. So here's a graph that I prepared earlier. First thing to ask is, well, what might the equation of this graph be? Well, actually it's quite hard to work out because I didn't take a photo of where that crosses the line. But first thing we do is say, what's the y-intercept? So where does this cross our line here? And then we could ask, what's the slope? Turns out the equation of this line is y equals negative 2x. Okay, so that's our equation. Now, what we're asking is, how can we find the value of a point on this line if we know the value of one of the coordinates? So for example, we could ask, when y equals negative 6, for example, what does x equal? And so what we can do here, if we're using the graph to find it, all we have to do is say, when y equals negative 6, 6 down, what does x equal? And it looks like it would equal, what do you reckon, negative 1.5 probably. And we can kind of confirm this with algebra. So we can sub in y equals negative 6 into this graph and say that negative 6 equals negative 2x minus 9. We can add 9 to both sides and say 3 equals negative 2x, and then say that divide by both sides by negative 2, which says that negative 1.5 equals x. So we can see that you can actually just read off the graph. And similarly, if we were to say, oh, when x equals negative 1.5, what does y equal? And you just say, well, let's go back 1.5, find the graph, and what's the y value? Negative 6. So that's a good way to do things. Another thing we can consider here is that simultaneous equations are when two lines cross. Right, so just say we've got two lines, something like this and something like this, and this could be y equals, I don't know, 1.5x plus 3, and this could be y equals negative 1.4x plus 10, or something like that. And you could say, solve the simultaneous equations. And what we could use the substitution or the elimination method. But when we're using graphs, all we have to do is say, well, if the solution set of this line is all the points along this line, and the solution set of this line is all the points along this line, at what point do these two lines share a solution set? and that's pretty clear. It's going to be there, and that if that's 3, 4, 5, 6, then that might be 6, 6. But using simultaneous equations, we could actually work out the correct answer, but that's just a guess. I'll take that away because that's not going to be right. I'll just say y value and x value, or something like that, and then we'd report that as x value, y value. Cool. So what are our applications for this kind of thing? Well, the first thing is to look at distance time graphs. So a distance time graph is basically just a graph that's going to look something like this. We've got some time and we've got some distance. And you could say at 2 minutes, or at 120 seconds, how far has the thing gone? And we could trace up, and we'd say, at 120 seconds it's gone 5 meters. Great. But there's one particularly cool thing about distance time graphs, and that's as follows. If we look at the gradient, what's the equation for a gradient? We usually talk about it as rise over run, right? And in this case, that would be the change in distance divided by a change in time. But if we think about what our units are, distance is in meters, right? And time is in seconds. So what we're actually doing here is just saying meters divided by seconds, which is just meters per second, which is the unit for speed. So it's pretty cool to realize that the gradient of a distance versus time graph is a speed. Hopefully that's pretty clear. And then we could kind of extend it a moment further and say, well, what if you've got distance time graphs for 2 objects? So we've got our initial object there, and then we've got another object that starts a bit further ahead. It may start at 2 meters or something, 2 meters ahead of the start line, and that travels in the same direction, but it's going a bit slower. It's got a lower gradient, therefore a lower speed, so it's traveling slower. We've got time and distance here. Well, we could ask, when do the objects meet? When do the objects meet? And we find that it's here. Because this is when they're at the same place, distance value, at the same time. They share a time and a place, time value. They share a time and a place, so they must be in the same place at the same time. They're meeting. Awesome. So that's kind of some applications, or one application of looking at using graphs to kind of interpret linear equations and linear solutions. And another one's break-even analysis. So break-even analysis. Well, first thing we can talk about is break-even point is when you have 0 profit, right? And so, what's profit? We can look at our cost equation, and we know that cost, the amount that it's going to take you to produce something, cost, is going to be a cost associated with each unit, and so we call that a variable cost. So if you're making a cake, this might be the cost of the ingredients for one cake, and the number of cakes, is X, and so we call this variable cost. We call this number of units. But there's also a fixed cost, right? And that fixed cost fixed cost is something that doesn't change no matter the number of units. See, for this is saying this is a variable cost, so for every additional unit we get an additional amount of the variable cost. But for the fixed cost, this is fixed. It doesn't change no matter how many numbers of units you use. That's why there's no x multiplied by the f. And this could be, if you're baking a cake, something like the cost of setting up your kitchen in the first place, because your kitchen can, if it's a good kitchen, put out heaps of really wide variety, or a large number of different cakes. But ultimately your kitchen cost isn't changing at all. So that's your cost equation. Revenue equation. Well, revenue is just how much you sell your cakes for, sale price, and your sale price, and then you're going to have times the number of units. So if you're getting $1 per cake and you sell one cake, you get $1. If you get $1 per cake, which is your sale price, and you sell 2 cakes, you're going to get $2. And then we can think of our profit equation. And our profit equation is just our revenue minus our cost. It's how much money do you make selling stuff, which is our revenue, minus how much did it cost you to make this stuff. So profit equals revenue minus cost. And our break-even point is when profit, we have zero profit. So from that we can say profit equals 0. Therefore 0 equals revenue minus cost. That's from here, from this equation here. And so we can actually just add c to both sides and say therefore cost equals revenue. So this is our break-even point, when cost equals revenue. And we can kind of think back to our simultaneous equations point here, where we've got a revenue equation and a cost equation. So if we draw our set of axes, and then we're going to have here dollars, and this could be dollars of revenue or dollars of cost, and here we've got x, or number of units. And so for our cost equation, we've got some f, some fixed cost, that even if you produce 0 units, you still have a cost, so it still costs you money. So you've got this one, and then it costs a bit of money to make each additional unit. And then I might actually do revenue in a different color. And then your revenue equation, there's no additional cost, which means there's no initial cost, should I say, which means you start at 0, but then hopefully you're going to be selling each unit for greater than the cost you to produce each unit. So the gradient of the revenue equation is going to be steeper than the gradient of the cost equation. It's going to go up faster. And so you're going to have an equation like it. You're going to have a line something like that. And so that's your revenue line, and this is your cost line. And say we sell a certain number of units. Say we sell this many units. Well, so what's the profit associated with that many units? Well, the profit is the revenue minus the cost. So this is your profit. Right? And if you sell at this point, well, here your cost is greater than your revenue. So you're taking a number and you're subtracting another number, so you get a negative. So here we're going to be making a loss. And so this is our break-even point. Break-even number of units, and that might be, e.g., 10 units. So this is how we can consider simultaneous equations. And you can see that I was talking before how the gradient of the revenue equation has to be greater than the gradient of the cost equation. Because if our gradient of our revenue equation wasn't greater, our revenue line would just go like that. If the slope was less, it would be there or somewhere around here. And so they'd never cross, and so you wouldn't have a break-even point. And then you probably wouldn't want to be making anything. Okay, now we're going to have a look at linear modeling. 2. So there's a few different things here that we're going to look at in linear modeling. The first is we're just going to have a quick chat about data. Now there's two types of data. It's qualitative. And you know, what's qualitative data? Well, that's descriptive data. So that's kind of like the test, the attitude survey you might have done at the start of this unit, where we said, you know, do you like maths? All those kind of questions, and you said, well, yes, I kind of like maths, or I strongly agree, I strongly disagree, that kind of thing. And then there's quantitative. And you know, it's kind of got the quality word in it. So you think of quality, it's not something you can kind of quantify in numbers, it's just something you feel. And quantitative is like quantity, it's like you're quantifying something that's really got numbers. So this is not descriptive, this is numerical. And of quantitative, so this is kind of like, you know, what did you score on your test? It's a number, it's a percentage, it's a mark. Here we've got discrete, just counting. So again, on your test, this minimum unit was half a mark. So we've got counting. You could have had 1 mark, 1.5 marks, 2 marks, 2.5 marks. It was counting. It wasn't the whole set of numbers. Or we can have continuous. And we deal with continuous quantitative data when we're looking at measurement. And so that's something like height. If we were to measure your height, we might think it was discrete because, you know, you're either 1 or 2 or 3 or 177, 178 centimeters. But actually, the value of a continuous measurement depends upon the accuracy to which you can measure. So we could keep on measuring, you know, 177 and 5 millimeters, or 177 and 5.5 millimeters, or 177 and 5 3/100ths of a millimeter. And so depending on the accuracy, we can keep on going to finer and finer detail, which is why it's continuous. Next thing to have a look at is scatter graphs. And so this is when we're comparing two variables, and we can call that bivariate data. So you might hear about bivariate data. That's all it means. Bi means 2. You know, bicycle, 2 cycles, 2 wheels. So we look at that when we're talking about bivariate data. So this is kind of, you know, we've got 2 axes, x and y. So what we're doing here is bivariate data. You know, you could have 2 things, again, like an x and a y. And x could be number of tutes attended, and then y could be something like score on assignment. And so you'd have we could have some scatter, something like this, right? And these are all people. These all represent people. So this person came to a heap of tutes and did really well on their assignment. This person came to quite a few tutes, you know, about half the tutes, if this is 100% of tutes, this is 100%, in which case we'll have to rub out these people because you can't get greater than 100%. This is 100% of assignment, so, you know, this guy came to a few tutes but did relatively well on the assignment. These 2 people went to rough with the same number of tutes, but this person did a lot better on the assignment than the first. And we could draw a line. I'll come back to a line of best fit. So this is a scatter plot. This is a scatter graph. Now we can have a think about our correlation coefficient. This is kind of another concept. Correlation coefficient. And so, what is a correlation coefficient? Well, correlation coefficient is just a number that helps us to understand how well data is correlated, or how well it fits a model. The model we're going to be talking about is a linear graph. So where a correlation coefficient tells us how well the data fits to a line, and R sits between -1 is smaller than R is smaller than 1. So R sits between the values of -1 and 1. And if R equals -1, we have perfect negative correlation. And so we think of that as something like this. You know, we've got some line, and then every point that we've recorded is exactly on the line. So that's perfect negative correlation, and they don't have to be spaced evenly, they just have to all be on the line. What about if R equals 1? Then we've got perfect positive correlation. And so that'd be something like, I'm sure you can work this one out, but we've got a positive line, right? And then we've got every point fits on that line. And then next thing is if R equals 0. And in that case we have no correlation. And so that's if we've got a whole heap of points. It could be in a structure like that, where it's clear that there's no line that would represent all points. If you did that line, there'd be equal points on each side. Did that line, you know, you could shift it anyway. Or we could just have kind of random, but in points in such a way that it's not clear which way you draw a line through this. I'm talking about this line, but I need to really link the line, talking about this line of fitting a line, back to the concept of line of best fit, right? And a line of best fit is just something we add by sight to a scatter graph. So you know, we might have a graph like this, and we'll have a whole heap of points. And we'd say, well, if we were going to draw a line that kind of cut the data in half, where would it go? And you know, for that data, I'd probably say something like that. So that's our line of best fit by sight. There are other methods to do lines of best fit, but we're not gonna look at them this week at least. And so if you could draw a line of best fit through this graph as well, and you could say, you know, there appears to be a positive relationship between the number of tutes you go to and the score you get on your assignment. And then the final thing we can look at is predictions. So the idea of predictions is that, you know, you can take a whole heap of data. So you can take a collection of data like this. This is all the students in a tutorial, and you say, can this data tell us anything, or can this data help us make any predictions? And if you can draw a line of best fit, if the correlation coefficient isn't 0, then you know, theoretically you can use it to make predictions. And the accuracy of your prediction depends on, you know, it is related to the R value. But you know, can we use what we've got to make predictions? And there's two types of predictions. So again, if we've got a graph, and then we've got a few data points, something like, so that's our data. So we can find a model, find a line that fits our equation, and we can say, you know, can we use this data to make predictions? Well, the answer is yes, and there's two different types of predictions. There is interpolation, and interpolation is when we're making predictions within the data range. So the data range here for x, which is the independent variable, in depth var, within the range of the independent variable. So if we say, if this is 5, if we're looking at 5, this is 5 units, so it might be, I don't know, how many years of school someone attended, and then this is related to their income or something. And we've got data for people who've had 1, 2, 3, 4, 5 years of school. So we're saying, okay, well, if the person had 3 years of school, what's their income? And the income here might be 50,000 or something per annum. And so using interpolation, we could say, well, from the data we draw a line of best fit. This line of best fit has an equation, which is y equals mx plus c, and we'd say if they had 3 years of education, what income would you expect them to have? And you could say, okay, well, we're going to take 3, the value 3, go up to the graph, and then look at the value, and that might be 40,000. And so that's how we can use interpolation within the data range, within the range, so the data goes from there to there, all this data here, to guess. And similarly, instead of just reading it off the graph, we could have just said x equals 3. The other method is extrapolation. And that's when we make predictions outside the x range, or the data range. And so that's anywhere from here onwards. And this is kind of less exact or reliable. And that's because past here, there might not be, the relationship that we see might not continue. If you've got, it might go like this, up, but probably more likely in the case of income, it's going to start to go something like this, and then it's going to really peter out. And there's going to be eventually very little relationship, because if you attend 1,000 years of school, or if you attend 20 years of school, for example, it's probably going to make that much difference between if you attend 20 or 18, so the relationship's going to weaken. So that's extrapolation. And extra means, extra or a little bit more or exterior to our data range, and inter is within, interpolation. So that's our kind of predictions. So that's what we've had a look at today. We've had a look at solving equations graphically, how we can kind of read off the equation how to find the data. We had a look at simultaneous equations and how they're a combination, or they're the shared point between two linear graphs. We had a look at distance time graphs, and we found out that the gradient, the rise over the run, is actually a speed. Looked at when objects will meet on distance time graphs in space and time. Then we had a look at break-even points and related them to simultaneous equations, and said that the break-even point is when our revenue equals our cost, and similarly our profit equals 0. And then just a quick look at some data things, at linear modeling, and talked about qualitative, quantitative data, scatter graphs where we compare two variables or compare bivariate data, correlation coefficient, how well does the data fit a line, and I forgot to mention this, we'll be predicting. So there are ways to calculate these things, but we'll just be predicting. And we've got perfect negative correlation, perfect positive correlation, no correlation. And then we looked at lines of best fit. And lines of best fit obviously are very related to our R values. And you could say, what's the R value of this line of best fit? And then talked about predictions. So making predictions within the data range or without outside of the data range, and the associated accuracy of interpolation and extrapolation. So that's the week 5 summary.